Number 10. Now we have vector the set S with two vectors. And part A, we want to describe the span of S. Now what I intended to ask here is for you to describe geometrically, because we all know what span is. You can say, okay, what is span of S? Well, that's all is the set of all linear combinations of those two vectors. Okay, so that's one way to describe. Okay, but geometrically, what is span of S? So you can say set of all linear combinations of 0 to 1 and 1, 0, 1. But to describe it better, you can draw, or at least sketch, the geometrical description of the span of S. So it's two vectors in R3, as we can see here. And so let's draw the first vector here. X is 0, y is 2, and z equals to 1. Okay, this is x, y, and z. So x is 0, so it's on the yz plane. 2, 1. So x equals to 2, and z equals to 1. So it should be this vector right here. Okay. And then the other vector is 1, 0, 1, x equals to 1. So let me draw with a different color here. Let's pick green. 1. And then y is 0 and z equals to 1. So that would be this vector right here. Okay. So the span of of those two vectors will be the plane generated by these two vectors, right? This first vector here will generate a line. The other vector will generate another line, and then all linear combinations are on the plane generated by those two vectors. Okay, so you can. So it's hard to draw a plane. I don't actually know very well how to draw the plane, but so the description is just a I guess this would be one way. That's the plane. It keeps going, right? It keeps going this way. That's part of the plane. That's not the whole plane. The plane is infinite. It keeps going forever. Okay, so you can say another description would be plane passing through vectors 0 to 1 and 1, 0, 1 and the origin. Okay. Any vector space, any subspace needs to contain the zero vector. Well, in R4.
Daddy!
Hello. How are you doing? Good to see you here. Okay, this is Isaac. Isaac just came in. Okay, go with mommy, okay?
Okay.
Close the door. Thank you. All right. Alright, so the description could be this one. Plane passing through those vectors, those 2 points in R3 and the origin. So that's the plane. Okay, that's part A. Part B, what vector can we add to S to make it span R3? Now, span of S is not R3, obviously. It's just a plane. So to get R3, we need an extra vector that is off the plane. So we need one more vector that is not on the plane. If it's on the plane, then the span of those 3 vectors will still be the same thing here, the same plane. So we need to pick up a vector. So we need a third vector that is not on the plane. Okay. Well, we've done this type of thing in class. You can pick a vector that is orthogonal to the plane. So you can find that by the cross product. Okay. So we can do that. Or you can perhaps do a little bit of trial and error. Right? So in other words, we want 3 linearly independent vectors, so you can do C1 0 2 1 plus C2 1 0 1 plus C3 ABC, because we don't know the third vector yet, equals to 0 0 0. And then when you get the matrix for this, would be 0 2 1 1 0 1 A B C 0 0 0. Okay. And then you have to play with these numbers. Now, if you look at the sketch here, I'm thinking that if you pick a vector that is maybe towards this way here, like a big vector that goes here, maybe negative x equals to 5, y can be small, maybe y can be 1, and the z can be negative 6, something like that. It looks like, try for example, put ABC here, negative 8, I mean not negative 8, sorry, positive 8. Okay. See, I want to try to get a vector off, maybe way over here, off the plane. It's hard to see from the graph, but you can try like 8, x equals to 8, the y can be 1, and the z can be negative. So let's try negative 6. And put those in here and see if this system has a solution, has the trivial solution. Okay, let's see that. Okay, I tried that. I put this vector here on this third column, okay, and put that in the calculator, and I reduce the matrix, and this is what I got. So yes, look at that. C3 equals to 0, C2 equals to 0, C1 equals to 0. So it's a trivial solution. Okay. Therefore, so those 3 vectors, 0, 2, 1, and 1, 0, 1, and 8, negative 1, negative 6 are linearly independent. Okay, see, I made a linear combination of those 3 equals to the 0 vector, and it's the solution for the C is not trivial if I use ABC equals to this. So therefore they're linearly independent. 3 vectors, that means I have 3 linearly independent vectors in R3. That has to be a basis. Okay, so those form a basis for R3. And obviously, if it's a basis for R3, it spans R3. Okay, just remember that another way of doing this is to get the cross product, okay? Do the cross product of these two vectors. When you do the cross product, you're going to get a vector that is not on the plane. In fact, it's going to be perpendicular to the plane. So we've done that in the class, and you can find out more about the cross product. And the vector obtained from the cross product is will make the set linearly independent, right? So if you pick those two vectors and the cross product vector, those three will be linearly independent. And you can put that in this form and try to find the C's. You will see that the solution is trivial, has to be trivial. Okay.